Welcome to today's lecture on Endfire array. We were discussing in the last class uniform linear array. Now, that has two varieties. One is broadside array that we have discussed. Today we will discuss the Endfire array. Now, physically what was broadside array? We were not giving any phase shift to each individual elements. So, that is why in the broadside direction all were getting interfered, the constructive interference, and the maximum was coming to the broadside of the array axis. Now, look at an Endfire. Suppose this is a array axis and I have elements here. Now, here suppose this is fed. So, everyone is getting fed. So, let us say this is I, this is I, this is I. Now, at any point in space, this I radiation that will give me, we know that this current into e to the power minus j k naught r by r. This also will that. Now, you see, if I want that the maximum radiation should be along this axis. So, I want, let us say here it should peak either here or this side. So, this one when it goes here, it has certain space phase depending on this distance, let us say this distance is r. So, due to this first one, what will be the field here? Far field will be I e to the power minus j k naught r by r into some constant, where this 4 pi etcetera everything will be absorbed. Now, what will be the next one? Next one will be this. So, next one will be the same k I e to the power minus j k naught r plus another distance minus j k naught, if this distance is d, minus j k naught d by that r plus d etcetera etcetera. Okay. Similarly, the other one there will be minus j k naught or minus j 2 k naught d, minus j 3 k naught d etcetera. So, you see that between this one and this one, the difference is e to the power minus j k naught d. Now, if while exciting compared to this I give a extra phase in the current of e to the power plus j k naught d, here I give e to the power plus j 2 k naught d, here I give e to the power relatively. That means, compared to this I am giving e to the power j k naught d, relative to this I am giving j 2 k naught d etcetera, j 3 k naught d etcetera in the excitation current phase, then this part is getting cancelled. So, each one will be now constructively adding. This is the idea of Endfire array. So, in the Endfire array, the progressive phase shift, which was our previous day's convention u naught, that we will have to choose as minus k naught d. That means, that to travel an inter-element distance, the space phase acquired by a plane wave, that we are negative of that we are giving as the progressive phase shift. So, always we know that major lobe maxima that occurs at u plus u naught by 0, this is from array factor we get. So, where will be the new, or I can say u max. So, u max will be now at minus u 0, and what is minus u 0? That is k naught d. That means, look at the diagram. So, now the main lobe is at k naught d, u naught k naught d. That means, just at the end of the visible spectrum. You see, half of the lobe is in the invisible spectrum. Okay. So, minus this is the Endfire array. Now, if I want it instead of this, I want it in the opposite direction. So, I will have to just change it. If I give it this u naught, if I give as plus k naught d, then this u max, or you can say u max 2, the second one, that will be at minus u naught, and that is minus k naught d. So, that means instead of this diagram, the main peak, that will be half of this main lobe peak will be here at that end. This is the Endfire array concept. So, and we can now find out the moment we have got this u max is k naught d. What was our u max? It is nothing but k naught d cos psi max, that is, I am taking this first one. So, k naught d. So, then I can say that from here it is apparent that cos psi max, that is 1, that means psi max is 0. So, what is psi? This is the array axis. So, psi is 0, that means with this was psi. So, psi is 0 means it is having the peak at this direction. Okay. So, major lobe occurs along the array axis. So, this thing you can see the array factor. Now, you see that the main lobe, if you look here, the main lobe is at the extreme of the visible space. So, there is a high chance you see that this next one, this is the grating lobe. This grating lobe can enter here, because this is already at the end. In earlier case, in for the broadside array, it was at in between. You see that it was in between, the main beam was in between. Here it has gone to one extreme. So, there is high chance that the next one can protrude for array, Endfire array. So, we will have to find out that to avoid grating lobes, what we can do, we know that the array factor is a periodic function, that we have said that array factor is periodic with a period 2 pi. So, we can say that minus u 0 minus 2 pi should be less than minus k naught d. What is the meaning? This is my minus u 0 and minus 2 pi, it will go here. So, this should be beyond minus k naught d, that means less than minus k naught d, that is the condition. So, to avoid grating lobe, I require this. So, for Endfire we have seen that u naught is how much? U naught is minus k naught d. So, that means putting it here, that k naught d minus 2 pi less than minus k naught d. So, if you solve this, this says that d should be less than lambda naught by 2. So, you cannot take d more than lambda naught by 2 for Endfire array. So, to avoid grating lobe, u should be always less than half of the operating wavelength. So, that means the length of the Endfire array generally is smaller than the length of the broadside array, because for broadside array, for avoiding grating lobe, you can go up to d, slightly less than d generally we take. But here you are, sorry, d means lambda naught, here it is half of that. And so, we can see how the thing looks like array pattern for an Endfire array is looks like this. These are the side lobes. So, you see x axis is the array axis and the main beam is along the array. Okay. It is a figure of revolution about the array axis, and we now need to find out the other parameters of this. The array factor we can write. What is the array factor of Endfire array? That is I naught sin n plus 1 by 2 k naught d. You see that u naught, I will put this thing, so it will come as cos psi minus 1 by this is the array factor. So, where is the main lobe? We have already seen where is the main lobe maxima occurs. Now, where is the main lobe null occurs? So, main lobe null. Obviously, when this thing will be plus minus pi, this argument, that means n plus 1 by 2 k naught d cos phi minus 1 will be plus minus main lobe. Other lobes you can find out, but main lobe is this. Now, for large n, what is the value of this cos phi minus 1 is plus minus, you put here k naught value to pi by lambda naught. So, you will get lambda naught by n plus 1 d. Now, you see for large n, this right hand side is quite a small number. So, that means cos psi, that value is 1 plus minus something. So, we can say that psi is near 0, and what is the value? We can say that the null at nulls, the value of psi is plus minus delta psi, where it is very small value. So, okay. Now, what is that value? Now, we will have to solve. Now, what is the value of this delta psi? So, I can draw this, that this is the main beam. So, this is at psi is equal to 0, we have seen the peak occurs, and this one is at plus delta psi, this one is at minus delta psi. Okay. Now, for small delta psi, we can write cos delta psi, that can be approximately written by series expansion as 1 minus delta psi square by 2, cos x is equal to 1 minus x square by 2. So, we can put that delta psi square by 2 is equal to lambda naught by n plus 1 into d, is not it? Because already we have found this cos psi minus 1 is this. So, equating this, we get this. So, what is delta psi? Delta psi is 2 lambda naught n plus 1 into d. So, what is our beam width? Beam width is, if we look at here, beam width, null to null beam width, I should say null to null beam width is 2 delta psi, and that is 2 into 2 lambda naught n plus 1 into d. Now, n plus 1 into d is nothing but the array length L. So, we can write 2 lambda naught by L per half. This L is nothing but the Endfire length, array length. So, we see that beam width of an Endfire array is inversely proportional to the square root of the array length, electrical array length or array length measured in wavelengths. Now, this was the for broadside, this was inversely proportional. This is inversely proportional to the square root of the length. So, that means the beam is not as narrow as the case was for broadside. So, here the Endfire it is not as narrow, but the point is this narrowing occurs in two planes, the greater beam width compensated by a narrowing of the pattern in both E plane and H plane. So, here you can say that suppose this is the dipole pattern and here this is not very narrow, sorry, this is array pattern, this is dipole pattern. So, pattern multiplication will give that I will have the resultant pattern like this. So, here both E and H plane patterns are governed by array pattern, and if n is large, the element pattern of half wave dipole has little effect here. So, mainly for Endfire arrays, the resultant pattern is both governed by the Endfire things. Now, we can come to the directivity. Now, for directivity, you see that let us estimate the directivity. So, for directivity, we take the array factor will be root 2 n plus 1, because there we take 3 dB things. Now, here we can put that where is the previously written array factor. Here all this we will have to put as cos psi half, if we call that. Suppose the angle at which the half power beam width become, let us call that psi delta psi half. Earlier for null to null we are calling delta psi, now it is delta psi half. So, here we will take several approximations. One is, this is already we have taken that, since for null to null delta psi that was small. So, delta psi by half will be further small. So, cos this minus 1, that we can write as minus delta psi half square by 2, and in the numerator this sine function can be approximated by numerator sine function, expand in a series expansion, take only 2 terms. So, what is sin x? Sin x is x minus x cube by 6, okay, and in denominator you have the sin k naught d by 2 cos psi minus 1. Now, cos psi minus 1, this is small, this multiplied by this overall thing is small. Here that overall was not small, that is why, because n plus 1 is there, that is why we have series expanded. Here we can directly write denominator will be that the whole sine thing will be k naught d, approximately the denominator will be k naught d by 2, then delta psi half square by 2, that means or equal to this is k naught d delta psi half square by 4. So, if you put it, there will be a bit manipulation, and also there is a quadratic expression will come, not quadratic, cubic expression will come. So, finally, we will get that this thing will be 1.63 1.63 lambda naught by pi d n plus 1 to the power half. Okay. So, this will be delta psi. Now, we know that what is the at which point half power things come. So, solid angle occupied by the main beam. So, you can write solid angle occupied by the main beam of the end fire array will be this, and what is that 0 to 2 pi, then 0 to delta psi half sin theta d theta d phi. Please remember this is not minus to this, because look at the end fire pattern. So, we have only this, suppose somewhere here will be delta psi half to 0, because the other half is not there for end fire in the visible space. So, this if you do, this is simple, because you now have the expression for this thing. So, that will be this expression you know. So, 2 pi 1 minus cos delta psi half, and that can be approximated to 2 pi delta psi half square by 2. So, it is pi half square. This is the solid angle occupied by the main beam. So, we know what is directivity. The isotropic radiator solid angle is 4 pi by this psi. So, that is 4.73 n plus 1 into d by lambda naught. This is the directivity of the end fire array. So, people have tabulated this, and suppose I take the number of elements, you have d by lambda naught, and what is the absolute value of directivity? Typically, let us take 6, d by lambda naught. Obviously, to avoid getting of this should be less than 0.5, let us take 0.4. This value turns out to be 11.35. If I make it 12, same 0.4, this will be 22.7. If I make it 6, but make it less, this becomes 8.51. If I make it 12, 0.3, 17.03. So, you see these are the typical values, some examples I have taken. Point is, this table underscores a designer's problem, that to get more directivity, you see from here that if I want to have more directivity, I need to increase d, but I cannot do it infinitely, my end is less than 0.5. So, that means to have more gain, you cannot do this, but what people have found out, actually that is a classical example Woodward Henson thing, that you do not put the main beam here, you actually this main beam you try to protrude into the invisible space, and by that actually you are losing the main beam, that means this energy you are losing, but also the total energy. So, the loss you are making, but the total radiated power, if that also goes down, because what is actually directivity? Directivity is the maximum radiation intensity divided by total radiated power. So, if you protrude main beam here, the total radiated power also will go down, and by that they have shown that you can increase the directivity there. So, that is called Woodward Henson technique for this, but that is a advanced technique. So, that is one way for proceeding for this Endfire array. So, this we have seen how to design arrays. You can have either broadside array or Endfire arrays, etc., and what is their directivity. So, required directivity you can find out what is the D, etc., that you need to do. In the next we will see that some other arrays which are useful, some other very simple type of these arrays which are also useful in some particular applications, and with that we end this array antenna lecture. Thank you.